Hi, and welcome to this lecture on lines in three-dimensional space. So here we have our three, x, y, and z, and then here I've sketched a line. And our goal of today's lesson is to learn how to parametrize a line using the vector equation of a line, and then from that we'll visit the scalar parametric equations, and we'll write down a few examples. In a future lesson, we're going to look at some more challenging examples, so in this lesson I really just want to focus on how to write down the equation based on some given pieces of information. So first of all, what pieces of information do you need in order to specify a line in R3? Well, if you stop someone on the street and say, how do you make a line? The first thing most people would probably say is that you need to have two distinct points. So one possibility is you have two distinct points, P and Q, and then through any 2 points passes a unique line. So those 2 points would determine the line. Then if the person you stop on the street is a high school algebra student, they might say something like, oh, you need a y-intercept and a slope. And that's correct. The more general viewpoint of that is you need a point and a sense of direction. In this lecture, we're going to have examples that are specified by one of these two conditions. We'll either have two distinct points or we'll have a point and a sense of direction. In R3, though, there are other ways to specify a line, other ways to provide information which would uniquely determine a line. For example, you could have two intersecting planes. Okay, so for example, I could have a plane that goes kind of like this, and another plane which intersects the first plane. The points they have in common, so the points that lie on both planes form the intersection, and then that intersection would be a line in R3. Okay, this picture is kind of dominating this slide, so let me shrink it, and then we'll go over the vector equation of a line in R3. For me, the most classical pieces of information that we would want to have if we want to write down the vector equation of a line would be the second possibility I put on this list, and that's that we would want to have a point and a sense of direction. So let's say the point, I'm going to highlight here by this green dot. And then our sense of direction is this vector that's telling us how the line moves away from that point. I could call that point, I don't know, P. But let's say the position vector for that point will denote by r subscript 0, r naught. So that's the vector that starts at the origin and lands on the point P. What I'm calling here the sense of direction is what we call a direction vector, and we typically denote it as V. And the vector equation of the line is r equals r naught, the position vector for the known point P, plus t times v, where t is just a scalar. The right-hand side is essentially a function of t, so we could also write this as r of t equals r naught plus tv. Now how this works is r represents the position vector for any point on the line. The idea is for every point on the line there's a value of t that would satisfy this formula. Let me call this q. So q is some other point on the line. When I made this graphic, I'm pretty sure I set q to be r naught plus 3 copies of v. So the position vector for q is r naught plus 3v. If this point over here is, say, capital U, then the position vector for u can be found as the vector sum of r naught minus 4 copies of v. So the right-hand side here is a vector sum. It follows the parallelogram law. And what this formula is telling us is every single point on the line satisfies r naught plus tv for some value of t. Notice the point P itself satisfies this equation with t equal to 0. The reverse is true as well. If you satisfy that equation for some value of t, you have to live on the line. Okay, let's work through some examples. So up here at the top, I've just repeated the vector equation of the line. So it's r, where that's the position vector for any point on the line, equals r naught plus tv, where t is a parameter that allows us to reach every point on the line. So first, let's just identify the key pieces of information in this example here so that we can write the vector parametric equation of the line which passes through the point P324 and which is parallel to the direction vector 1, -1, 5. Okay, we have our known point P. That means that r naught is the position vector for P. So the coordinates of r naught are just 3, 2, 4 written as a vector. The phrase parallel to the direction vector 1, -1, 5 is giving us our sense of direction. Don't get too distracted by the language parallel to this other vector. What this means is that if I were to draw this vector, 1, -1, 5, typically I would draw it at the origin. It might look like this. But a vector is a length and a sense of direction. It's not anchored to a point in space. So I can treat my direction vector for my line is equivalent to that vector. Right, so written in coordinate forms, we might want to graph the vector 1, -1, 5 at the origin. But when I do the vector sum of r naught plus t times this vector, in order to actually do the sum, I have to take the tail of that vector and put it on the head of r naught. So we're going to end up moving that vector up to the line when we take the vector sum. So all that to say that our direction vector v is just going to be the vector 1, -1, 5. That's what's giving us our sense of direction. For every 1 unit you move in the positive x direction, move 1 unit in the negative y direction, and go up 5 units in the z direction. That's our direction that we travel when we travel along this line. Okay, so now we can say our line is r equals r naught, so 3, 2, 4, plus t times v, so 1, -1, 5. Let's continue with this example in order to define a different set of equations which also describe the same line. So to repeat what we just found, the vector parametric equation of the line passing through the point P parallel to the direction vector 1, -1, 5 was this. Here I've written it as r of t. Again, that's optional. It depends if you want to view the left-hand side as a function of t. I typically do, but you don't have to. Okay, let's take this equation, which is the vector form, and rewrite it as a set of scalar parametric equations. Okay, so let me just rewrite the equation we have. I'll write it as r equals 3, 2, 4 plus, let me go ahead and do the scalar multiplication of that second vector with the scalar t out front. So that would be t, -t, 5t. Now let's do this vector addition. So we have 3 plus t, 2 minus t, 4 plus 5t. Any value of t that we plug into the right-hand side is going to send us to a point on this line where 3 plus t would be the x-coordinate, 2 minus t would be the y-coordinate, and 4 plus 5t would be the z-coordinate. So the scalar parametric equations are parametric equations for each coordinate, each x, y, and z coordinate. So in particular, we'll have x equals 3 plus t, y equals 2 minus t, and z equals 4 plus 5t. It's important to treat this as a set. It doesn't make any sense to just say x equals 3 plus t and not also provide the information for y and z. We're traveling along a line, so as we travel along it, the x, y, and z coordinates all need to be given to us. So you want to think of these three equations together as also describing the same line as this vector equation at the top. We can summarize the scalar parametric form with the following set of equations. So if r naught is the position vector x naught, y naught, z naught, meaning that x naught, y naught, z naught correspond to a known point on the line. And if our sense of direction, our direction vector, has coordinates a, b, c, then the scalar equations are x equals x naught plus at, where t is the parameter, y is y naught plus bt, and z is z naught plus ct. So again, those three equations taken all together describe the line. Okay, let's solve a problem here. So does the point -1, 8, 5 live on the line which in vector parametric form is given as r equals 1, 0, 1 plus t times -1, 4, 2? Or does the point 6, 2, 3? So here are just 2 points. Pretty sure one of them lives on the line and the other one doesn't. How can we figure this out? And what we can do is use the scalar parametric equations to see if there's a value for t. Once we set up x naught, y naught, z naught, and abc with the values 1, 0, 1 and -1, 4, 2 given to us from the vector parametric form, once we plug all that in and set up our scalar parametric equations, can we find a value of t which, when plugged into these three equations, sends us to an x value of -1, a y value of 8, and a z value of 5? And is there a different value of t perhaps that would give us 6, 2, and 3 for those three coordinates? Okay, so can we find t so that -1, which would be the x coordinate, could be written as 1 minus 1t. So again, here I'm using the fact that 1, 0, 1 is like x naught, y naught, z naught, and -1, 4, 2 in the above equations play the role of a, b, c. Okay, so our x equation is -1 equals 1 minus t. Can that be true at the same time as the equation 8 equals 0 plus 4t? And also at the same time, can it be true that 5 equals 1 plus 2t? So here this is x, this is y, and this is z. If the point -1, 8, 5 lies on this line, then all three equations must simultaneously be true for the same value of t. Okay, probably the easiest one to work with is that middle equation. So if it's the case that 8 equals 0 plus 4t, then that means t equals 2. So let's plug that value into the x and z equations. We get -1 equals 1 minus 1 times 2. That's true. So that seems promising. And 5 equals 1 plus 2 times 2, which is also true. So the three scalar equations are all simultaneously satisfied for a t value of 2. So the answer to the first question is yes. The point -1, 8, 5 lives on that line. In fact, it could be written as 1, 0, 1 plus 2 times -1, 4, 2. Okay, let's try the same process for the second point. If you want, you might want to pause the video and try to work it out and see what you get. Okay, so can we find t so that for x, we have 6 equals 1 minus t. For y, we have 2 equals 4t. And for z, we have 3 equals 1 plus 2t. Okay, once again, that middle equation is the easiest thing to work with, so this suggests that t would have to be 1/2. It must be 1/2 in order to have the middle equation true. Can the first and third equations be true? Now if we plug this into the x equation, we get 6 equals 1 minus 1/2. That is false. So the answer is no. The point 623 does not lie on this line. Let's finish this lesson with 2 more examples. First, let's find the vector equation of the line passing through the point 242, which is parallel to the z-axis. We'll find the vector form, and then we'll write down the scalar parametric equations. And then for our second example, we'll find the vector equation of a line which passes through 2 points. So that was one of the other characterizations of a line we gave at the beginning. If you've got 2 distinct points, then there's exactly one line that passes through both of them. Okay, starting with the first example. The phrase here we're most interested in is parallel to the z-axis. So we have our known point, and this is our sense of direction. So the question is, how do we describe this sense of direction with the direction vector? And there are infinitely many things that you could choose. They just have to be vectors which are parallel to the z-axis. So I'll choose v to be the vector 0, 0, 1, in other words, the k standard basis vector. But you could have picked 0, 0, 50. You could pick 0, 0, negative pi. All of those would work. They would all be vectors that would point you in the correct direction. Okay, so our line is going to be r equals the position vector for the known point, so that's the vector 242, plus the parameter t times our direction vector, 0, 0, 1. So that's the vector equation. For the scalar equations, we now just go component by component. If we look in the x-coordinate, we have 2 plus 0t, so x equals 2 plus 0t. Y equals 4 plus 0t. And z equals 2 plus 1t. Of course, it'd be simpler to write x equals 2, y equals 4, and z equals 2 plus t. Had I picked 0, 0, negative pi to be my direction vector for this line, my first 2 equations would be unchanged, and my third scalar equation would be z equals 2 minus pi t. That set of equations would still describe the same line. Okay, this first example was an example of having a point and a sense of direction. Let's look at the other condition that we said we would have in this lecture, and that is a line passes between 2 points. So from P to Q, let me try to sketch this. Let's say this is P, and this is Q. They both live on the line in question. So in the previous example, we just needed 1 point and a sense of direction. Here we have 2 points. We'll pick one of them to be our known point, let's say P, and then our sense of direction is the vector PQ. So with those choices, R0, the position vector for a known point on the line, will be the position vector for the point P, so 0, 2, negative 5. Okay, so our position vector comes from the vector PQ, because the vector PQ points us along the line. So that's going to be the vector 7 minus 0, 1 minus 2, 10 minus negative 5. Or in other words, 7, negative 1, 15. Okay, so the vector form of the line, the vector equation, is r equals the position vector for the known point, so 0, 2, negative 5, plus the parameter t times the direction vector 7, negative 1, 15. And then the scalar equations are x equals 0 plus 7t, y equals 2 minus 1t, and z equals negative 5 plus 15t. Okay, that wraps it up for this lecture on lines, but we will return to this after we've done a lecture on planes. I would like to do some more challenging examples where we mix together lines and planes. For example, if I flip back to where we started, we've done a couple examples where we had conditions 1 and 2, but we haven't yet talked about how you would parametrize the line which is characterized as the intersection of two planes because we haven't seen planes yet. So we'll come back to this and look at some more examples later. Thank you for your attention.